Welcome back. Here we are continuing with chapter 11, gases. And you already saw the first recording, which was a basic introduction to the chapter itself and to make you realize that you already know how gases behave. All we're doing is bringing a framework within science so you can understand it and explain it better. So to continue doing that, we are going to be talking about these topics. So the first one will be the kinetic molecular theory, which we already mentioned on the first recording. And that can be used to describe the properties of gases, which you already know are going to be pressure, volume, the amount, moles or grams, and the temperature. In relation to that, we're going to see how pressure, which is one of the properties of gases, is defined as a force acting on an area. And then we're going to see how we have to spread that in numerical terms by using pressure units, the most common one being 1 atmosphere, based on the amount of air that we have on this planet. Once we do that, then we are going to talk about the empirical formulas, which are formulas based on experiments, which allow us to relate these four properties. And one of them is going to be Boyle's law, another one will be Charles' law, another one will be Avogadro's law, the ideal gas law, the combined gas law, and the Dalton's law of partial pressures. And once we do that, we're going to go back to what we did like 2 chapters ago when we talk about limit and reactance, percent yield, theoretical yield, and so on. And we're going to be learning how to do that using gases and the properties of gases. Because as you notice one more, gases are defined by pressure, volume, amount, it could be moles or grams, and temperatures. So knowing these three allow us to know the moles, and then we can do stoichiometry using the properties of gases. So that's what we're going for the rest of this chapter. So let's begin with the kinetic molecular theory and predicting the main properties of gases. We already talked about this on the first video you saw, but once more, if we have a gas, let's say this is a cloud of gas, it's made out of particles. Those particles can be molecules, can be atoms, like the noble gases. But the main thing is that would be a representation of gas made out of particles. So the first thing we have to do is fix that, because that would be a bad representation. Because one of the things that we know about the kinetic theory of gases is that the space between the particles is going to be huge. So I cannot put too many of those particles in there because they're very separate to each other. So the space between the particles is huge compared to the volume of the particle. So the size of the particle itself is super small compared to the empty space between them. Because of that, those particles will rarely interact with each other because they will never see each other. And as long as there's some temperature in there, as long as the temperature is above 0 degrees Kelvin, these particles are going to be moving. And they are going to be moving in random directions. So we don't know which way they're going to be moving, just that they're moving. And if the temperature goes up, then they're going to move faster. And I'm doing that with a longer arrow because if they're moving faster, they're going to travel longer distance on a shorter time. So if these two particles were to collide, their collisions are not going to absorb any energy. So we're going to call that a elastic collision. It's like when you are playing a pool, when a ball hit the other ball, imagine all that energy being transmitted to the other ball without slowing down, without friction or anything like that. So in addition to that, so we see that as we increase the temperature, the speed of the molecules increases. So because of that, if these particles were inside a container, if the particles were inside a container, when they move and happen to collide with the container, that force there, that's what we call pressure. So the higher the temperature, the faster they're going to move, and the pressure will be higher. So as you notice, what I'm doing is predicting the properties of gases based on the kinetic molecular theory, which tells us there's a lot of space in between. The molecules or particles rarely interact with each other. When they hit the wall of the containers, that's what we call pressure. They move faster with higher temperature. So because of that also, if this was a balloon instead, if these particles are hitting the walls, then the balloon will begin to expand because the particles are pushing outwards. So we can see, because of the movement of the particles, which move faster with higher temperature, if the balloon is expandable, if the container is expandable like a balloon, then the walls will start moving outward, therefore increasing the volume. So we just described how temperature relates to volume, how the pressure relates to the temperature, and so on. So with the kinetic molecular theory, you can predict the different properties of a gas. Higher temperature, molecules are moving faster. If the container is expandable, they will push the walls out, so it gets bigger. If the container doesn't expand like a metal cylinder, then if the temperature goes up, then the particles will hit the walls harder. They cannot move the wall, so the wall is going to feel all that power, so the pressure is higher. And in relation to pressure, let's define pressure in terms of a force hitting a surface. So if I have a force hitting a surface, imagine a container like that, and I have my particle, and the particle is moving, then it's going to feel a pressure there. And if I have more particles, let's say 3 particles, and all of them are hitting that surface, because the particle is big, the pressure is going to be distributed in several different places. But what if the area is a smaller area and I still have my 3 particles and all of them are hitting within that small area? Now, with the same force, we are assuming all of them are at the same temperature, so they're moving at the same speed. Now the area is smaller, so the pressure is going to be concentrated on a smaller area, so you will have a higher pressure. That's why if I have particles moving inside a balloon and they're hitting the walls in all random directions, if I made this balloon smaller, and the particles are still inside, right? Then we're gonna discover that the pressure will increase because now the area is smaller and the particles are hitting in there. And if you don't believe me, go get a balloon, fill it up with air, and then force it to be smaller. And let me know if the pressure inside the balloon is increasing or not based on what your hands feel. So, so it's super easy to understand gases if you just think about the balloon and play like a kid. So with that information and what you saw in the first lecture, you should be able to answer this daily work. And you should be able to answer this daily work also. Because we just did that. And with that, pending more reading on the textbook and practice on Alex, you should have a pretty good understanding of the kinetic molecular theory of gases. And you should be able to use those postulates of the kinetic molecular theory of gases to explain, for example, why a balloon will get bigger when you increase the temperature, talking about kinetic energy of the particles and so on. So we're ready to move into a new topic. Identify and explain the relationship between pressure, force, and area. We just did that. So that's the example I just gave you with the big square and the small square, big area versus a small area. So if you have to go back a few slides, feel free to. What we're gonna be concentrating now is how to express those numbers into units. So let's do that. So what is pressure? We already explained pressure. Pressure is nothing more than a force acting on a surface. And because these particles are moving, they're gonna hit a surface with a specific area. So when they hit that there, they're gonna bounce back, but the force that's gonna be felt by that area, that's what we call the pressure. Is the force acting on an area. In terms of the gases, we call pressures every time a particle collides with the walls of the container where the gas is. That's what causes pressure. That's what pressure is. And we can measure pressure in several different units. For example, we can measure it in atmospheres. And let's explain briefly what one atmosphere is. So for example, you live inside a circle, or actually you live on the circle. And we call that circle planet Earth. And there's air around that ball of dirt. So inside here, we're going to have our planet, and there's air around it. Like we said before, we're going to call this Earth. So all this air is made out of particles. So all that air is going to be made out of particles. So one thing that you can say is you were standing on planet Earth, all that air is going to be on top of your head, being pulled down by the force of gravity. So imagine having 20 books in top of your head. Would you feel the weight of those books? Yes. So that would be the pressure. However, imagine all the air that's around this planet on one specific spot in top of your head, like it is right now. All that weight is what we call 1 atmosphere of pressure because the planet has 1 atmosphere. So, so when we talk about that, that's what we call 1 atmosphere. There's another measurement to measure pressure. We set that 760 millimeters of mercury is the same as 1 atmosphere. And this is the way we understand this. Imagine you have a container, and that container contains liquid mercury. And then you take a test tube, for example, upside down, and you put the test tube inside the liquid mercury. And you are doing this on top of a bench on your kitchen or a classroom or something, which is exposed to air. So like I said before, that air coming all the way from the edge of the planet is pushing down into the mercury. So all that matter, all the oxygen, all the carbon dioxide and all that is being pulled toward the ground by the force of gravity. And that's putting weight on the mercury, so the mercury gets compressed, but it finds a way to escape, and it goes up the tube. Having the proper dimension of the test tube when they do these measurements, the mercury goes up the test tube, and it's going to get up to a point. So it's going to get up to whatever point that is. And at that point, it's going to measure 760 millimeter of height. And remember, 1 atmosphere of pressure is what is coming down and putting pressure in top of the mercury. So we can say that 1 atmosphere equals 760 millimeters of mercury, because that's how high the mercury goes due to that pressure. So that's something we do. We have different ways to measure 1 atmosphere. We can measure it based on how high the mercury goes, how much mass you have, and so on. So what we're going to have is the standard would be 1 atmosphere, which is going to be the same as 760 millimeters of mercury, which is also the same as 760 torrs. This is another unit the engineer used, which is also the same as 101,000 pascals, and so on. So on your textbook, there's a table in there that tells you all the things that are equivalent. And notice that I said 1 atmosphere of pressure equals 760 millimeters of mercury. Another way to say that is 1 atmosphere is the same as 760 millimeters of mercury, or you can say 760 millimeters of mercury is the same at 1 atmosphere, which is nothing more than 2 conversion factors, which tell us we can change from one measurement of pressure to another measurement of pressure by using the train-track method or dimensional analysis. So let's do a few of these. I don't have the table with me at this moment, but you have it on your textbook, so you can find it. Or if not, you can find it on the internet. So let's do the ones I remember from memory. So let's change. So we change into atmosphere, 1277 millimeters of mercury. So given 1277 millimeters of mercury, can you tell me how much is that in atmospheres? Yes, I can, because I don't care about the millimeters of mercury, right? Because I'm looking for atmospheres. And according to the conversion factors I just showed you, 1 atmosphere equals 760 millimeters of mercury. So it's nothing more than 1277 multiplied by 1 divided by 760. So that's one way of doing one of them. And whatever that is, you can put it on your calculator. What about pascals? If I have 2.38 10 to the 5 pascals, can you tell me how much is that in atmospheres? Yes, I can. Because since I don't care about pascals, because I'm looking for atmosphere, according to my table, 1 atmosphere equals 101,000 pascals. So this is nothing more than 2.38 10 to the 5th multiplied by 1 divided by 101,000. And double check that number when you see your table. Hopefully my memory is working right. What about PSI? Well, I don't remember that one from memory, so you're going to have to check that one on your table. But I remember torrs. So given 455 torrs, can I find atmospheres? And I will have to say, yes, I can, because I know that I don't care about torrs, right? Because I'm looking for atmosphere, but 1 atmosphere is 760 torrs. So it's the same value as the millimeters of mercury. It's just a different way the engineers express it. So that's all it is. You just need the table that gives you all the equalities, which is on your packet, on the one we've been using for the test, on the conversions. And you just set up the train track method, and you're done. So with that said, you are ready to do this daily work. And once you do that, we talked earlier about the relationship between force, which is the movement of the particles. The faster they're moving, the stronger the force. Pressure, which is the impact that is felt when they hit a specific area. And you can relate that to the area. If you have the same amount of particles, the smaller the area, the higher the pressure, because the particles are going to be hitting on only one area instead of spreading the force over a bigger area. And now you also know how to convert between pressure units, given the table that you have on your conversion tables. And once you do that, we will meet again to talk some more about gases, and we will be talking about some of the laws. We will begin with Boyle's law and Charles' law. So until the next one, see you soon. Take care.